Hello everyone, I am Nicole Harrison with the National Renewable Energy Laboratory, and I'd like to welcome you to today's webinar hosted by the Building America program. We are excited to have Catherine Court, Joseph Peterson, and Thomas Culp here today to discuss low E storm windows and window attachments. Before we begin, I'll quickly go over some of the webinar features. For audio, you have two options. You may either listen through your computer or your telephone. If you choose to listen through your computer, please select the mic and speakers option in the audio pane. By doing so, we will eliminate the possibility of feedback and echo. If you select the telephone option, a box on the right side will display the telephone number and audio pin you should use to dial in. Panelists, we ask that you please mute your audio device when you are not presenting. If you have technical difficulties with the webinar, you may contact the GoToWebinar help desk for assistance. If you would like to ask a question, please use the questions pane to type in your question. Please indicate which speaker you are addressing your question to. If you are having difficulty viewing the materials through the webinar portal, you may find PDF copies of the presentation at the website listed here, and you may follow along as our speakers present. The associated case study is also posted there. Today's webinar is being recorded, and the recording will be available on the DOE YouTube channel within a few weeks. We have an exciting program prepared for you today that will discuss how window attachments and coverings, such as storm windows and cellular shades, can be a cost-effective means of reducing energy use in residential buildings. This webinar will review some of the latest research in this area, including results from Pacific Northwest National Laboratory's controlled Lab Homes 2015 experiments examining interior low-E storm window inserts and cellular shades. The webinar will also cover recent related activities by utilities, energy efficiency programs, and the recently launched Attachment Energy Rating Council, AERC. Before our speakers begin, I will provide a short overview of the Building America program. Following the presentations, we will have a question and answer session, closing remarks, and a brief survey. The U.S. Department of Energy's Building America program has been a source of innovations in residential building energy performance, durability, quality, affordability, and comfort for 20 years. This world-class research program partners with industry to bring cutting-edge innovations and resources to market. Visit our website at buildingamerica.gov to find more information about the program and the Building America Solution Center, which provides expert information on hundreds of high-performance construction topics, including air sealing and insulation, HVAC components, windows, indoor air quality, and much more. Building America is supported by 10 industry research teams and 4 national labs. Each of these teams and labs partner with dozens of industry professionals, including builders, remodelers, manufacturers, and utilities. The best and the brightest in the residential buildings industry can be found here. And now on to today's presentation. Our webinar today is High Performance Enclosure Strategies, Part 2, Low E Storm Windows and Window Attachments. If you would like more detailed information about this effort, please feel free to contact our speakers. Our first speaker today is Catherine Court, a research economist with Pacific Northwest National Laboratory. Katie is an economist with PNNL and team lead of Building America's Window Retrofit Solutions program. She has over 15 years of experience analyzing energy efficiency programs, technologies, and research, and provides technical support for the Department of Energy's Building Technologies program. Our next speaker is Joe Peterson. Joe joined PNNL in the summer of 2012. He serves as the primary technical lead and point of contact for work done within the PNNL Lab Homes. He has a master's degree in electrical engineering and completed his thesis on Lab Homes research techniques to simulate human occupancy in a controlled experimental setting. Our final speaker today is Thomas Culp. Thomas is the owner of Birch Point Consulting, LLC, which provides engineering and strategic consulting services in the areas of energy-efficient window performance, building code development, glass performance, and glass coatings. With that, I'd like to welcome Katie to start the presentation.
Show my screen. Thank you, Nicole. And thank you very much for joining us on our presentation on energy savings from window attachments. Okay. There we go. Hopefully everybody can see the screen. I'm Katie Court, Catherine Court, commonly known as Katie. I am speaking to you today from our Richland, Washington, where Pacific Northwest National Laboratory campus is located. I'd like to recognize some members of the team who have been working with window attachments, including Joe Peterson, who Nicole mentioned we'll be talking to later. Joe is our on-site engineer and principal investigator for the lab homes experiments, which we have conducted this year, focusing on insulating cellular shades and interior low-E storm panels. Also on the team is Tom Colt from Birch Point Consulting, who is our resident expert on all things window attachments, and coatings related. And Tom is going to be talking to you a little more about, a little more in depth about the technologies, how they work, and some of the field studies and modeling studies that have been conducted in this area. I would also like to recognize some of our partners, Quanta Technology, who provided the interior insulating panels for the lab homes experiments, and also Hunter Douglas, who provided their Arctella Triel insulating in cellular shades for the lab homes experiments. And pictured to the right there is part of the Hunter Douglas team, including Stacy Lambright and Drake McGowan. We are very happy to have joint funding for our experiments this year, including both Department of Energy's Building America program and the Northwest Energy Efficiency Alliance, or NEA. NEA being an alliance of energy efficiency organizations and utilities here in the Northwest, dedicated to accelerating energy efficiency for both commercial, residential, industrial, for both gas and electric here in the Northwest. They're taking a look at window attachments for application in both potential application in both commercial and residential buildings. And just so we are clear on what I'm talking about when we use the term window attachments, I've taken this table here from the efficientwindowcoverings.org website. This is a website that was developed by DOE and Lawrence Berkeley National Laboratory and Building Green to provide information, overview material on an assortment of different window attachments, and allows someone to compare these products in terms of a variety of different characteristics, including energy performance, privacy features, installation cost, that type of thing. So if you see on the left, I've highlighted with the red arrow the attachments that we will be talking about today, including exterior low-E storm window attachments. We have a lot of past research we'll be talking about and field studies, and then two interior attachments, these being the insulated window panels and the insulated cellular shades, which were the subject of our lab homes experiments this year. The data from this pie chart here is taken from the Residential Energy Consumption Survey that DOE conducts periodically, and I think it's interesting to know we've been looking at this data through the years, and what we've seen is that the presence of single pane windows in homes has persisted over the past 2 decades, despite the fact that there are approximately 30 million windows that are replaced each year with higher performing insulated windows. In addition, the homes that have the single or that have the double pane windows, percentage of these have windows that are not necessarily the high performing low-E windows, but rather clear glass windows. So we see a tremendous opportunity for technologies that improve existing window performance, such as energy efficient window attachments, to provide energy savings to a large segment of the residential homes. Just to drive this point home a little more, it's probably not a mystery to anyone that windows are a major source of heating losses and gains in a building. Just how much, if you take a look at some of the component load studies that LB&L conducted a few years back, it was estimated that there were about 25 to 30% of the heat losses, and this would be both for commercial and residential buildings. Those heat losses are lost through infiltration and conduction through the window. Even a larger percentage of heat gains comes in the cooling season. So this, with the windows being a large source of heat gains and losses and through all seasons. And also interesting to note that when you take a look at newer buildings, which they did as part of the component load studies, and you tighten up the shell quite a bit and bring the insulation levels and the roofs and walls and floors up to a code level, even improve that window to a low-E double pane window, you still have on a component load basis those windows accounting for about 60% of your heat losses in a building. So their point here being that if you were wanting to reduce the heating and cooling load of a building, you really need to mind the gap. You need to look toward the opening in the shell, and that's really what window attachments are focusing on. And not only can they reduce the energy consumption in the building, but they can do it, what we're finding, in an affordable manner. Often window attachments will meet the savings to investment ratios and payback thresholds for a lot of the different weatherization and utility programs that are out there. They can be applied to existing homes, and they are can be easy to install, so sort of a lower installation cost. And I don't have it listed here, but it's equally important, is they can add to the comfort of a home and the aesthetics. For a lot of energy efficiency types of measures, sometimes you will have the homeowner begrudgingly installing them just for the energy savings, but for window attachments, there's an actual aesthetic appeal in that they improve the look of the home both inside and out. And so this is a very important feature that comes along with window attachments. In this slide, I'm featuring the comprehensive modeling study that was conducted by LB&L with assistance from DRI that looked at 11 different window attachments in 12 different climate zones, and looked at the energy savings potential in all these different climate zones. And the bottom line conclusion is that yes, there is a great deal of energy savings potential from window attachments. Of course, how much depends on the type of attachment, the season, the climate, and the operation of these attachments. But two kind of standout window attachments that were consistently saving energy, particularly in heating-dominated climates, were the low-E insulating storm panels and the insulating cellular shades. And that's part of the reason why we have focused a lot of our initial efforts and validation studies on these two technologies. As part of our efforts related to window attachments, we've also done some market assessments and identified some of the market barriers to window attachments. This has driven a lot of the activities that have taken place in this program, so I'm just going to go through a few of these. The first one being the identity, what we refer to as the identity crisis. This is has to do with the fact that window attachments often kind of slip through the cracks between insulating measures and windows. And so they're often not recognized by a lot of utility weatherization programs, or even by consumers when it comes time to upgrading the energy efficiency of their home. The second one has to do primarily with storm windows, and that's a stigma barrier, in that most people know what a storm window is. They've been around forever and ever, and they have a picture of what a storm window is, but the picture they have is probably of their grandmother's storm window, the older generation of storm windows, which were maybe not so attractive, aluminum frame, had to be removed each year and had a tendency to get dirty and needed to be cleaned, that type of thing. And so one of the challenges with this window attachment is sort of overcoming the picture that people have in their head of what a storm window is and introducing them to the modern storm window. And that has some newer features. The third barrier is the fact that window attachments are not recognized by any sort of rating system. So unlike windows that have an NFRC rating or insulation that is rated for its energy performance, there is no equivalent rating for window attachments. And energy efficiency organizations and consumers have, increasingly rely on these types of ratings to make some of their decisions. And so not having this, again, we see as a market barrier. The fourth one is the do-it-yourself barrier. This, in one sense, implies that these are low cost and easy to install, which is a good thing. It means that most of these are actually installed by the homeowners as do-it-yourself products. But that also means that it might be relegated to that list of do-it-yourself projects that just never gets done. And also implies that there's really not a very well-developed third-party installation network for some of these products. This is not so much the case for window shades and blinds that has a pretty well-established third-party installation network, but it can be a problem for some of the other window attachments. The final barrier has to do with permanence and persistence. This is a very big deal for utility programs, that when they incentivize any sort of measure, they want to ensure that that measure saves energy persistently over time, and that it is installed and operated in a manner that will save energy over time. The perception by most utilities is that window attachments are not necessarily installed permanently and not necessarily operated in a manner that saves energy over time. So that's another issue that we want to address with some of our programs and studies. So how we're going about addressing some of these barriers. The first bullet here is has to do with the Rating Council, and that DOE, to address the fact that there is no rating for window attachments, has launched the Attachments Energy Rating Council. This is a council has been set up as an independent public interest nonprofit organization whose mission is to rate and label and certify the performance of window attachments. The purpose is to provide accurate and credible information about the energy performance of window attachments, which will help consumers make informed decisions about window attachments. And we're really excited about the launching of this council, and the expectation is that they'll have a couple of products rated by the end of next year, 2016. So we're looking forward to those results. They also have a new website, which I've listed there, that you can check out if you want more information. There's also work being done by the Consortium of Energy Efficiency to develop tools and resources related to window attachments, including some product overview guides, and these are available on the CEE site as well. We've made some efforts to try to integrate window attachments into some of the building energy simulation software and audit tools that are out there, which now largely just aren't even set up with a framework to examine window attachments, and this ends up being a barrier when it comes to audit. So one of the things that we've done is have successfully integrated it into the Facility Energy Decision System model, which is the FEDS model, used to support a lot of federal energy audits. And so now when audits are performed storm windows now come out as a possible measure for a retrofit measure in some of this modeling work. And then finally, we've had some successes working directly now with utility and weatherization programs. Most notably here this past year, working with the Regional Technical Forum, which is a policy advisory forum in the Pacific Northwest. It's staffed with a technical crew, and they help identify regional priorities and make recommendations for energy efficiency measures, in particular for Bonneville Power Administration. And so working with them, we went through their process and were able to get low E storm windows adopted as a proven measure in the Pacific Northwest, which means that some of these different utility programs can now integrate low E storm windows into some of their energy efficiency programs. And finally, I just wanted to bring up the fact that we're amassing quite a bit of a library of resources in this area. Tom and Joe are going to talk a little more in depth about some of these more recent studies, but this is just to kind of call your attention to the fact that if you are looking for information in this area, there's a chance or need to pull out some numbers or look for some something specific to your region even. Chances are there might be some information in some of these resources, which I have listed in more detail at the end of the presentation. So with that, I am going to turn things over to Tom Culp.
All right.
Now I'm clicking.
Okay. Thanks, Katie. As she's giving me control, as we hand that over, I'll be talking a little bit about some of the technologies, how they work, and then kind of the development from the initial concept to lab testing to field studies to now we're at the stage at like wide-scale deployment, and to get a little bit of history of how these technologies have advanced. Let me make sure if I got control now. I'll be primarily talking about low E storm windows. I'll mention a little bit on the insulated cellular shades, and then Joe, who will be following me, will talk a little bit more about some of the specific studies, both for low E storm panels and interior panels, as well as the cellular shades. All right, let's see if this advances. So before I dive into the details, I did want to spend a moment talking about what low E storm windows are and what they are not. And Katie mentioned this briefly. There seems to be a lot of misperception where people remember their grandmother's old storm windows that had to be put up in the fall and then taken down in the spring. And we really want to emphasize that modern storm windows and panels have significantly evolved and are not your grandmother's old storm windows. Modern storm windows and interior panels are designed to blend in with existing architecture, be permanently mounted, and are available as both fixed and operable windows. So, for instance, the photo on the left shows interior low E panels, both fixed and operable. And the photo on the right shows operable exterior low E storm windows, including insect screens. And as you can see, they're aesthetically pleasing. These are white, but they can come in any color. They're slim, and they are in many ways hard to distinguish from the primary windows. So as we'll talk about, low E storm windows and panels are a great new tool for updating the energy performance of existing windows without the full cost of window replacement. And it talks about it up there that the cost can be 1/3 or even 1/4 of full window replacement, yet get to a similar level of performance. But we did want to emphasize that, of course, if your existing window is deteriorated, the frame is rotted out, you have other problems, then replace it and use as high of a performance window as possible. But where it's impractical or undesirable to replace the existing window because of either cost or historical considerations, then low E storm windows are a very good option. So now to go through a little bit of the history and how these technologies work. First, like the initial concept came up in the late 1990s when Lawrence Berkeley National Lab suggested that low E storm windows could be a cost-effective insulating and air sealing measure for the existing windows. And basically the premise is that, first of all, it acts as an air sealing measure for your primary window. We always worry about in energy and weatherization programs about sealing the rest of the home, rim joists and so forth. And then, but very little is done about the window except maybe around the perimeter. The window itself is usually left there as a very leaky source of air leakage. And applying a panel can significantly reduce the air leakage through that primary window, and we'll talk about some of the results we saw in the case studies. You also create a dead air space, a space between the panel and then the primary window, and this reduces conduction and convective heat losses across the primary window. And then finally, with the addition of low E glass, you reflect radiant heat back into the home, so you reduce the radiative heat loss out that window. And so using low E glass versus just regular clear glass, you can have a 35% improvement in performance. So these images here, they're from heat transfer modeling using the Therm software from LBNL, showing the temperature profiles. On the left there, we have the single glaze fixed wood window showing the very cold glass temperature, which not only is an indication of the heat loss, but it also can form condensation or even ice on that single pane. In the middle, as you add a clear glass storm window, you now create that airspace and you are insulating it more, and you significantly raise the temperatures, helping to reduce that condensation, but also reduce the heat loss. And then finally, the last step on the right, when you add the low E glass, then you now are reducing the radiative heat loss as well, and you can warm that glass even more and cut heat loss even more. And you see this in real life as well. So this is an image, an IR field image taken from the outside of a home. So light colors show heat loss. And there's 3 windows here. In the center is the original single pane window, a picture window. And then on the left and right are 2 windows that have had low E storm windows added over them. And as you can see, it's very clear that the low E storm windows on the left and right have significantly reduced the heat loss outside that window. Now, the other technology we'll be talking about today are insulated cellular shades. That these are another, new measure for significantly improving the energy efficiency of existing windows, and they operate in many ways by some of the same premises. So this is a product from Hunter Douglas, Architella Triel honeycomb fabric, and if you look on the left image there, you can see that it's multiple cells within the cellular shade. There's actually 5 air spaces in there, so that will reduce your conductive and convective heat loss across that space. In addition, the blind is again up. There's an airspace between the blind and the window itself. And then finally, and it's a Mylar. This image does not show it, but this product also comes with an option to have a Mylar metallized film on this interior cell, which acts as a low E layer, again reducing radiative heat loss across this space, and lowering the U factor or increasing the R value of the overall assembly. And when you look at IR images, we see a similar story where, in this case, on the left window shows the primary window with no window covering, significant heat loss. The same window with the insulated cellular shade, dramatically reduced heat transfer and heat loss out of that window. This particular image and the insulating benefit, of course, has a primary benefit in the winter, where we can see significant heating savings. Katie talked a little about the overall, how windows contribute a large percentage of the overall heat loss out of the home. This can significantly reduce that. On the cooling side, cellular shades also play a significant role in that. During the summertime, that solar gain is unwanted, and cellular shades have been shown to reduce unwanted solar gain through the windows by up to 80%, so significantly reducing your heat gain and your the cooling load that must be supplied to the home. Joe will talk a little bit more about the cellular shade testing that's been done in the last part of this presentation. Now, speaking about low E storm windows again, don't worry, I know this is a cluttered big table. This is more here for your later reference. We often get asked, what is the performance of a a low-E storm window over different types of primary windows. People are used to, or they're learning about U factors for new windows. So what is it when you put a low-E panel over an old existing window? So this is a paper that was just recently published through PNNL. The reference number's at the bottom, and it's at the end of the presentation as well. And it's also based on some prior work we did with ATI test lab that did simulations using window and therm software to calculate the performance of low-E panels over different types of primary windows. And so, for instance, in that first top chunk, you see for a single glazed wood window, the U factor can be reduced from 0.88 down to 0.34 or 0.36 for a low-E storm window, either on the outside or the inside. And in general, we see that over single pane windows, the U factor decreases about 60% by the addition of a low-E panel, so very significant. Over double pane clear glass windows, so these double pane windows that are older, don't already have low-E glass, the U factor decreases between 43 and 57% with the addition of a low-E panel. And then the normal low-E glass that's used in these also reduces the solar heat gain by about 17 to 28%, depending on the specific window type. And that's with the regular low-E. In addition to that, there's also a solar control low-E option that's available. It's a similar low-E glass, but has a slightly tinted look to it. It provides a little bit more solar control. So if you're in the southern part of the country, you can look at that as an option. That'll lower the solar heat gain even more. And there it goes, and this is just a similar table, even busier for over metal frame products. But again, this is for your later reference, but we see similar performance improvements. So moving on, LBNL came up with this concept, did some initial calculations, and we've done some of these more recent calculations that show, yes, this should work. So the next step is let's test it. Let's see, does it work under real-life conditions? So the first step was in 2002, LBNL used their mobile window testing facility, or MOA facility. So this was, it can be moved, but it was stationed up in near Lake Tahoe, Nevada, up in the mountains for cold weather climate. And it has two bays where you can do side-by-side instrumented testing of different window options. And in this case, we have one bay that has had a single pane window and then a low-E storm window added over that, and then it's directly compared in side-by-side testing with a new double pane low-E replacement window. And this data on the right, the details don't matter, but basically this is the instantaneous heat loss through each of those windows. The bottom line shows the single pane, and then the gray and black dots up above it are the side-by-side comparison of the low-E storm window and then the brand new double pane low-E replacement window. And as you can see, the improvement is basically the same. So this was very promising that, hey, yes, this concept does work. A little bit later, LBNL, together with Building Green, did some calibrated IR imaging, this time from the interior. This is showing an interior on the left, showing an interior low-E panel over a vintage single-pane wood frame window. And on the right is those single-pane sashes were replaced with double-pane low-E argon sash inserts. These are taken from the interior, so in this case dark colors show heat loss. And as you can see, the two options behave fairly similarly. We're getting similar improvement from either replacement sashes or from a low-E panel. And in fact, when you look around the perimeter, the low-E panel is actually doing arguably a little bit better around the perimeter just from the air sealing versus the sash inserts. But again, the main point is that it shows you can get similar performance with a low-E storm window or interior panel. So really the next step was, okay, let's scale this up. Let's look at what happens when you put in a whole home. So in 2003, 2006, DOE, HUD, NHB Research Center, and LBNL conducted a field study on 6 weatherization homes in the Chicago area, bungalows type homes where all with single glazing and then with the addition of low-E storm windows. The details are in the paper referenced at the end, but the heating load of the home on average was reduced by about 21%, which gave a simple payback period of about 4.5 years. So very cost effective. Additionally, we did blower door testing, and in this case, we saw an overall home air leakage reduced by 6 to 8% just by adding the exterior storm windows. Nothing else was done in the home, no other air sealing. This shows how in these older homes, the primary windows can be very air leaky, so just adding a storm window or panel to that can significantly reduce the air leakage of the entire home, which contributes to the energy savings. So we followed this up in 2011-2013 with a similar study in Atlanta, this time still within HV Research Center, but this was DOE funded, and then we had industrial partners with Larson Manufacturing and Quanta Panel, where we did a similar study in 10 older homes with single glazing around Atlanta. We wanted to test a warmer climate with a mixture of both heating and cooling seasons. By adding low-E storm windows, these were all exterior low-E storm windows, over the single pane windows, we saw approximately 15% heating savings, and then on the cooling side, we saw a range from 2 to 30%, which is very large variability. And we believe this large variability happened because these are old homes in established neighborhoods where you have a lot of variation, not just in orientation of which way the home is facing, the windows are facing, but also the degree of trees around there, tree coverage and shading. So we saw energy savings in all cases, but it did depend on the specific situation of the home. Heating savings were more consistent. Again, we saw significant air leakage reduction just by adding the panels. In this case, these homes were older and leakier, and we saw 17% average reduction, which was 3.7 air changes per hour. And that, for those of you who get involved in new construction, that should surprise you a little bit, because the modern building codes require new construction homes to have total home air leakage less than 3 to 5 ACH. And just by adding the storm windows, we were able to reduce these homes' air leakage by about that much. So that showed the original homes and the original windows are that leaky, so that the opportunity of adding a storm window can make a significant improvement in air leakage and energy savings. Now, in addition to the energy savings, we also were careful to do some occupant surveys to look at other attributes as well. And it kind of came out surprising that everyone appreciated the energy savings, but that's not tangible. So actually, all these items actually ranked higher to the occupants than the energy savings they saw, which number one was improved home appearance. These are older homes, beat up windows, and by adding an exterior storm window, you actually improve the aesthetics. They also commented on reduced drafts, improved comfort, presumably thermal comfort, and then finally reduced noise, because adding that second panel improves the acoustics, especially for single pane windows. And then part of this same research funded by DOE with NHV Research Center, Quanta Panel, and Larson, we addressed two large multifamily buildings in the Philadelphia area. This is just one of the two buildings. They're identical, side by side. They're 3-story large buildings with 101 total units. They already had very old, beat-up, clear storm windows over single glazing and metal frame windows, so not very efficient. And so we wanted to test, okay, what if you take these old style storm windows and replace them with new modern design low-E storm windows on the outside? These are exterior windows. In this case, we saw a 20% reduction in the heating energy use over 2 heating seasons, and then we saw a 9% reduction in the cooling energy use. And similarly to the single-family homes, when we did blower door testing on individual apartment units, we saw an average air leakage reduction of around 10%. So this was interesting because, like I said, baseline was not single-pane windows. The baseline was single-pane windows with these old-style clear glass storm windows, and which it shows that as we've gone to more modern, newer design windows, there are benefits in energy consumption, not just from the low-E glass, but also just from air tightness and design of the windows. So it's a very positive study. Another point we wanted to make was that low-E storm windows, even though a lot of the studies have been kind of on these older buildings, and that is the focus, low-E storm windows and panels are not just for low-income weatherization homes. They are a good retrofit option for windows to upgrade your existing windows in almost any building type where it's impractical, too expensive, or undesirable to replace the existing windows. And these are all real-life examples, courtesy of Quanta, where this includes homes of all types, historic buildings. This is a historic library in the upper center. Historic homes where under certain historic covenants they're not allowed to replace the windows, and even large buildings. This building on the right is I think it's 26 stories. It's an old bank building in Hartford that had single pane windows. It would have been cost prohibitive by far to replace the facade on that, so instead they added low-E interior panels on the inside, and it's being converted to residential apartments. So it's a good option in many cases. So we've done some of the modeling. We did some field studies. So the next step, as we've kind of scaled from the lab to field studies, is how do we go into broad application, expand the use of these more broadly. And so that's where programs come in, not only education programs such as today with Building America, but also working with weatherization utility programs. Katie spoke about what we recently working with the Regional Technical Forum out in the Pacific Northwest with the utilities. Another aspect was back in 2009, the ability to include low-E storm windows was added to NEAT and weatherization assistance software. And on the side, please let me know if you would like instructions on how to do that within NEAT. I have kind of a little handout on how to do it. But this is software that's used by many state weatherization programs. And so in 2010, Pennsylvania added low-E storm windows to their weatherization measure priority list for single-family homes. And this followed a NEAT analysis for 37 home types that cover the range of housing across Pennsylvania. And we saw the SIR, or savings to investment ratio, range from 1.3 up to 2.2 over different window types. And this savings to investment ratio, if you're not familiar with that, must be greater than 1 to qualify as a cost-effective measure. Basically, you're getting more time value of money back versus over the compared to the initial cost of the measure. As you can see, these are all very well cost-effective, and these were done with low natural gas pricing. But a number of these areas use propane fuel. In other parts of the country, you still see electrical resistance heating. And when you have higher priced fuels like that, the SIR is even higher. It's even more cost-effective. And then with support funding from Building America, PNNL, and I was involved, we did calculations expanding this NEAT analysis, also doing it using ResFin, which is another software package from Lawrence Berkeley National Lab, to expand this analysis to 22 cities across all 8 climate zones, all the way from Zone 1 in the southern tip of Florida up to Zone 8 in Alaska. And these are in the paper numbers are down below, 2 studies, one in 2014, and then we recently updated fuel prices and dove into the data a little more. This was just released this month. You can look up these paper numbers, and the references are at the end as well. And so the details are in the papers, but in general, this is a kind of a summary slide for overall single pane windows and double pane metal frame windows. It was shown to be cost effective in climate zones 3 through 8, which is the blue line up, with the SIR, or savings investment ratio, ranging from 1.2 to 3.2. Again, this is with natural gas, with propane or electrical resistance heating, it'll be even higher. In about the upper 2/3 of the country, just regular low-E storm windows is recommended. And in this south central area, kind of between the blue and the green lines, solar control low-E storm windows are recommended, because there you have a balance of both heating season and cooling season. South of that, in the very far south, mostly Florida and the Gulf Coast, we have solar control low-E storm windows still offer significant energy savings and benefits, but you need to look at it on a case-by-case basis. This is a similar chart, but now over double pane wood or vinyl frame windows. So now in this case, your primary window is already a better performer. It's still not up to par with modern low-E windows, but it's a better performer, so your cost, your energy savings are a little different, and your cost effectiveness is a little different. In this case, we found it was cost effective in climate zones 6 through 8, as well as the eastern part of zone 5. And of course, it'll be recommended over an even larger range where you have propane or electrical resistance heating. Now this study, we also want to emphasize that it's very common when you talk about window technologies and people talk about cost effectiveness, they talk about the cost upgrade of choosing a better window over a baseline window, and they don't talk about installation cost. This is the fully loaded cost effectiveness, including the full product and the installation costs. So this is actually being quite conservative. If you've already chosen to do a storm window, then the cost effectiveness of choosing a low-E storm window is even better. And to make that point, here's some charts from this recent paper where on the top, this is the fully loaded cost effectiveness, including installation costs, where of course your energy cost savings are the highest in the colder zones, and this is split into the base energy savings plus the air leakage savings. And then as you go to the southern zones, we still have significant energy cost savings, but it goes down. And similarly, the payback period is shortest in those northern zones, but it's cost effective in basically zones 3 through 8. But that's the fully loaded cost. And so if we, like similar to other measures, look at just the incremental cost of using low-E glass versus clear glass as a short payback period in all climate zones over all window types. So if you've chosen to do a storm window, it always makes sense to do a low-E storm window. So with that, I'm going to hand it over to Joe. Joe Peterson's a Pacific Northwest National Lab. He's an engineer who is the technical lead on the PNNL lab homes, and he'll talk a little bit about the controlled testing done on some of the low-E storm panels, as well as give more detail on the cellular shade studies. So, Joe.
Thank you, Tom. As Tom said, we've done a lot of research related to interior and exterior storm windows. So now what we need to do is a little bit more focused study on the evaluation of these windows in the lab homes. So the unique thing about the PNNL lab homes is they're 2 double-wide homes that allow for technologies to be integrated into one and then have the 2 homes be compared side by side. So it allows for a very controlled simulation of each of these technologies. So these homes were specifically developed to be representative of the Pacific Northwest and the climate that we've seen in this area. So some of the initial partners that we have that are part of the PNNL lab homes, Building America and the City of Richland and Bonneville Power are some of the most notable ones. So here's an aerial view of the PNNL campus. The blue box there is where the lab homes are located. As you can see in the bottom left, we have the climate zones. The star is where Richland, Washington's at, right near the Washington-Oregon border in climate zone 5, like I said. So the basic characteristics of the lab home. So it's a 3-bedroom, 2-bath, 1,500 square foot, factory-built, manufactured home to the HUD code. Within both the heating and cooling season experiments, we have the ability to introduce heat in a couple different ways. So during the cooling season, we have a heat pump that cools the lab homes, and then during the heating season, we generally use a forced air furnace because it's 100% efficient, and we also have cadet wall heaters that can supply supplemental heat to the space. So we have R22 and R11 walls in the roof and in the ceiling. So the window area we have is 195 feet squared, or 13% of the floor area. So this note here right below is, and I'll talk about this a little bit more later, only 74% of the windows, or 144.8 feet squared, were covered by our interior low-E storm windows. And I'll talk more about that later, but basically why that is that Quanta does not make a interior storm window large enough for these sliding glass doors. We have incandescent lighting and other things that you would normally find in a manufactured home. We have a bath, a kitchen, whole house fans, refrigerators, ranges, and dryers, but mostly these are not powered on or run when we're doing some experiments. So within the homes, we have extensive metering and monitoring technologies, not only for the power, but for the dynamic heat flow through the space. And I'll talk about that a little bit more too. So here's the floor plan of the lab homes. As you can see, there's 3 bedrooms and then the living space. If you look at the top left, we have the different technologies that were integrated and kind of where they were throughout the home. So I'll start first with the orange bars. So those are the interior low-E storm windows. So those were placed on 74% of the window area within the lab homes. So you can see those in the master bedroom, bath, and so on. The blue square is the Hunter Douglas cellular shades. Those were on all of the window areas within the home. So you can see Hunter Douglas has the ability to manufacture these cellular shades large enough to cover these really large sliding glass doors. So that was nice. The blue or the green bar is the sliding glass door retrofit. So due to the fact that Quanta does not make interior storm windows large enough to cover the sliding glass door, we needed a way to kind of eliminate some of that window area. So what we did was we took a bunch of bad insulation and reflective coating insulation and kind of effectively blocked off the window. This was to reduce infiltration, reduce solar heat gain, and all the light effectively coming through that window. So if you look at the other sliding glass door here, this one did not have interior storm windows retrofit on it, and that comes into play when we look at some of the savings, because this is facing west, and when the sun sets, we'll get a lot of solar heat gains associated with this. So we'll talk about that a little bit later. So the metering and monitoring within the lab homes. So we have 42 individually controllable breakers, and what that means is they're all motorized and can switch off and on via a predefined schedule. So that's how we integrate some of our occupancy, being light bulbs or introduce heat to the space with our cadet wall heaters. We also have a bunch of temperature and relative humidity sensors throughout the homes. So 15 interior temperature thermocouples. So those are all the ambient temperature thermocouples that kind of give us a dynamic flow of heat through the space. 22 interior and exterior glass surface temperature thermocouples. This is actually going to be increased based on some of the studies that we've done here, just so we can make sure we understand the temperature on different surfaces of the primary window and the low E window. We have 2 relative humidity sensors, 2 mean radiant temperature sensors, some water things that aren't really applicable here, but we have that capability. The data logging technology that we use is Campbell Scientific CR1000s. And this gives us minute data, 15-minute averages, or hourly averages. So we'll talk more about that later when we talk about some of the savings. So here's the basic window characteristics. As I said, so the baseline home is made to be representative of the Pacific Northwest. So we have a double pane clear glass windows with an aluminum frame. And those are the baseline windows. And you can see in the table below the U factor, solar heat gain coefficient, and the visible transmittance of each of these. So when looking at the low-E storm windows, interior low-E storm windows behind the baseline windows, we can see a reduction in the U factor, solar heat gain, and visible transmission. And we also see that for the patio doors too, even though we weren't able to actually test that. So basically what this equates to is, with the interior low-E storm windows, we see about a 53% reduction in U factor, 19% reduction in solar heat gain coefficient, and about a 17% visible transmittance. Just as a comparison, we have the R5 triple pane argon windows that were studied by Sarah Witter, who's also at PNNL. And as you can see, they're significantly reduced the solar heat gain and U factor, but it's just, you know, a good middle ground that the Lowy storm windows gives us. So installation of the interior storm windows. So if we look at the top left here, generally what you take is a measurement of the bottom sill and the vertical and horizontal, and that's the measurements that are sent to the manufacturer. And what they do is they, you know, generate this track that the Lowy storm windows can slide in and out of, and this track has a seal around it, a rubber gasket that fits into the seal. So fairly easy to install. Use a blind stopper as shown here to try to get them about, an inch from the primary window, and then screw the track into the sill. And then it's fairly simple to just place the panes in there, and generally the low E coating is facing out of away from the conditioned space. So in general, these can go over trim. Unlike the exterior storm windows, they don't have any weep holes or anything like that. And in general, if you have a really leaky home, these will help increase the air tightness for that home. So here's some simple infrared images that we have of the master bedroom. These were taken in during the heating season, so in the winter, as you can tell. So the first column is the baseline home, and then this one is the experimental home. The experimental home has the low E storm windows installed in them. So you can see these are the exterior infrared images. So you can see on the outside we have about a 43 degrees Fahrenheit for the baseline home with just the standard baseline windows, and then a 39.4 degrees Fahrenheit with the low E storm windows installed. So that's a temperature delta of about 3.6 degrees Fahrenheit. And like Tom said, that's due to the low E coating reflecting some of that conditioned heat back into the space and trapping it. So similarly, if we're looking at the interior of the space, this is the same window just from the inside. We can see the baseline home at about 60 degrees Fahrenheit for the surface, and the experimental home at about 66.6 degrees. So almost a 6.7 degree difference between the two. So the baseline home, the heat transfer between the primary window is a lot. So it's losing a lot of energy and a lot of heat through the window, and that's kind of mitigated through the low E storm. So can we validate, or can we kind of validate some of those infrared images with kind of some advanced metering techniques? So what we tried to do is we wanted to get kind of the complete picture of the dynamic flow of heat from the internal conditioned space to the outside ambient air temperature. So what we have here is at the top the interstitial space temperature, which is the temperature between the primary window and the low E window. Existing window exterior surface temperature, so that's the outside temperature of the panel of the primary window. Existing window interior surface, so this is the temperature of the low E window interior space. Interior storm window surface temperature, so this is the temperature seen at the conditioned space. And then this is the data logger that we had. So basically what we can see is exterior glass temperature comparison during the heating season. So we have the average outdoor air temperature during this day was 40 degrees. So what we can see is Lab Home B, that is the experimental home with the low E storm windows. Lab Home A is the baseline home. And what we're looking at is the outside surface of the primary window. So we see that Lab Home A is significantly warmer than Lab Home B on the outside surface of the primary window. And that's exactly what we saw with the infrared images. Similarly, if we look at the interior of the space in the interstitial space, we can see the same thing that we kind of saw with the IR images. The experimental home, lab home B, is 4 to 6 degrees warmer than the baseline home, lab home A. That's because the low E coating is reflecting a lot of that internal heat back into the space. So yeah, and as you can see, we have the interstitial space here, which is at an elevated temperature and things like that. So this gives us a nice dynamic presentation, or a good story as to how the low E storms can save energy and, increase the comfort in the space. So over the course of the heating and cooling season, we did a couple different experiments, and here's some of our findings. So the average savings for the low E storm windows was 8.1% annually, when we were specifically looking at coverage of 74% of the window area. This could be more if we had both the sliding glass doors covered with an interior storm window or an exterior storm window possibly, but this is compared to 12% for a triple pane primary window. So the experimental periods, as you can see, during the summer cooling, we have the storm windows in lab home B as the operational scenarios. We saw an average energy savings of about 4.2%. In the winter heating season, we saw about 8.1%. In general, we use Energy Plus models to kind of extrapolate this into an annual savings number, and we found that to be 7.8%, plus or minus 1.5%. For comparison, here's the R5 results that were brought by Sarah Witter, and these were about a 12.2, plus or minus 1.3%. So not quite as good, but comparable, given that we only had 74% of the window area covered. So these are the HVAC load profiles over a representative day for both the heating and cooling season. And though these graphs show continuous lines, these are actually the hourly average values for the HVAC load. So on the y-axis, we have watt hours. On the x-axis, we have time in hours. And then on the secondary axis, we have temperature in degrees Fahrenheit. The dotted line here is the outdoor air temperature. And then these two dotted lines are the internal temperature. And our internal set point for both heating and cooling season was 71 degrees. So during the winter, so during the heating season, you can expect most of the heating to be done in the morning due to the fact that, that's when no sun's out, no solar gains are expected. So we can see a peak reduction in HVAC load between the baseline home, which is in blue, which has no window attachments, and then the experimental home, which has the low E windows on it. So we can see a basic reduction in HVAC load that continues throughout the day. As the temperature increases throughout the afternoon, the solar gains associated with the envelope heating up reduces the need for heating. And then in the evening, you can see that lab home, or the experimental home, stays warmer longer than the baseline home, and that's due to the fact that the low E coating and extra pane of glass is trapping additional heat within the space. So on the second graph here, this was in the summer, so in the cooling season, similar, we have watt hours on the y-axis, hours on the x-axis, and then temperature. Dotted line is the outdoor air temperature, and then the other two dotted lines are the internal temperature, hovering around our 71 degree set point. So in the morning, you would expect no cooling to be going on, and then you can see as the envelope heats, a peak load reduction due to the interior storm windows between the baseline home in blue and then the experimental home in red. Then you can see a similar operation throughout the evening as the afternoon/evening. And one theory for this is that the interior storm windows can only offer so much benefit, and as the envelope heats up to 85, 90 degrees, the gains associated with the envelope cause the the two homes to perform similarly for part of the day, and then you can see in the evening a similar trend. So the next thing that we evaluated was the Hunter-Douglas honeycomb cellular shades. And due to the functionality of these cellular shades, they can automatically be moved up and down via predefined schedules. And this is done through motors within the actual blind themselves. So it's actually quite handy to program schedules into via an app into some Hunter-Douglas technology, and then these blinds will follow these schedules. So there's a couple things that we wanted to test given the advanced functionality of these shades. So the first one was the optimum operation. So that the optimum operation is the implementation of the Hunter-Douglas HD green mode. And what this is it's roughly based on the solar calendar and then the geographical location of where the blinds are going to be installed, so the latitude, geographical latitude. And this not only has to do with the optimization or reduction in the heating and cooling loads, but it's also for the customer to we need to introduce light into the space and things like that. So that's also taken into account, because the insulating values of these shades, it would be the most optimum operation for them would be down all the time and closed. But obviously that isn't a real world application. So during the optimum operation, we had the Hunter-Douglas shades being operated to the HD green mode, and then the baseline home had no window attachments at all. So what is the added benefit, or what is the reduction in HVAC load that we can see for that? The second one was cellular shades compared to standard vinyl horizontal blinds. So that in this experiment, we have the Hunter-Douglas blinds operating to the HD green mode, just as in the other operational scenario, and then we have the baseline home with the standard vinyl horizontal blinds operated to the same HD green mode. So we can this will give us another metric of comparison between the Hunter-Douglas blinds and the standard vinyl horizontal blinds. The third measurement scenario that we have is the static operation mode. So in general, what this is both window attachment technologies, the Hunter-Douglas blinds and then the vinyl horizontal blinds, remain closed for the full duration of the day. So this is an attempt to get at the insulating values associated with each of the technologies. So it's important when we go forward looking at these different scenarios to keep in mind what the baseline technology is for comparison. So HVAC energy saving is generally based on the operational schedule and the baseline technology. So here's just a general overview of the experimental period, the operational scenarios, the number of experimental days that were in the experimental period, the baseline technology, and then the average energy, HVAC energy savings seen from this. So as you can see on the first one, the static operation, this was done in the cooling season, so during the summer, 14 experimental days, and the baseline is compared to the standard horizontal vinyl blinds. So we see the Hunter-Douglas blinds having a 13.3% reduction in HVAC loads when compared to the standard vinyl blinds. The second one we have the summer cooling season. So this was optimum operational comparison. So both the Hunter-Douglas blinds and the standard vinyl blinds were following the HD green mode operational schedule, which is based on the solar calendar. We could see that the Hunter-Douglas blinds outperformed the standard vinyl blinds by about 10%. And then we have the winter heating season, so this is in the winter. And then the optimal operation, this is the baseline is no window attachments in the baseline home, and then Hunter-Douglas honeycomb cellular blinds operating in the HD green mode in the experimental home. So we can see, 17.6% reduction in HVAC energy load just based on a baseline home with no windows attachments. So looking at each one of these scenarios, we have a representative day that's kind of gives us a little information or a little background on kind of what's happening. So as with the other ones, we have time on the x-axis in hours. We have watt hours, HVAC energy usage on the y, and then on the secondary axis we have temperature. Now remember again that this, even though it shows it's continuous, these numbers are hourly averages, so it's just these are actual watt hours. So we have the baseline home, which has the standard vinyl. Oh, excuse me, no, it doesn't. We have the baseline home, which has no window attachments on it, and then we have in blue, and then we have the experimental home in red that has the Hunter Douglas blinds operating to the HD green mode. So as you can see that most of the operation is done in the morning, and this, you can see a peak load reduction associated with the Hunter Douglas blinds when compared to the standard baseline home with no windows attachments. So, experimental period of 9 days and then 17.6% savings of HVAC load. The second one that we're looking at is the static operation in the cooling season. So during this experiment, we have the baseline home, which is in blue, has the standard horizontal vinyl blinds completely closed for the duration of the day, and then the experimental home has the Hunter Douglas honeycomb cellular blinds closed for the remainder of the day. We have outdoor air temperature, and as you can see, this is a relatively warm day in Tri-Cities, and then we have the purple and turquoise lines are the internal temperature of each one of the lab homes. So as you can see, in the morning, we would not expect any cooling to be happening, but during the day or as the envelope begins to warm up, we see a peak load reduction associated with the insulating properties of the Hunter Douglas cellular shades, and that remains throughout most of the day, even when we get really high peak outdoor air temperature. And as you can see, during the latter part of the day, the experimental home, which is in turquoise here, has the Hunter Douglas cellular shades on there, and it stays warmer longer than the baseline home, which is the standard vinyl horizontal blind. So that that's attributed to the insulating values and the shades being able to trap a lot of that heat within, or a lot of that conditioned air within the space. So finally, we're looking at the cooling season optimum operation comparison. So what this is the baseline home, which is in blue, has the standard vinyl blinds, horizontal vinyl blinds operated to the Hunter Douglas HD green mode, and then the experimental home, as before, has the Hunter Douglas cellular shades operated to the HD green mode. And as you can see, during the morning, no cooling load is required. During the mid-morning and early afternoon, we see peak load reduction associated with the operation of the Hunter Douglas cellular shades, and that remains throughout the rest of the day. So 7 experimental days, and the benefit of the Hunter Douglas cellular shades was about 10.4% in HVAC load savings when compared to standard vinyl horizontal blinds operated in the same way. So remaining research questions and things to think about as we move forward. So operation and automation. So as we've seen in the previous graph, that the automation and operation of the window attachments can greatly influence the HVAC load, specifically when it comes to the Hunter Douglas blinds and the HD green mode. And then what value does this have to the to not only the consumer, but to utilities and other people. Other things to think about is coverage optimization. So where is the best place to put these Windows attachments if not 100% of the window area can be covered at one time? One would think that east and west facing windows would probably be better for low-E storm windows or shades to optimize or reduce solar heat gain as needed. Optimizing return on investment, minimizing costs while maximizing benefit. What other window attachments are there that perform similarly at a different price range or things like that that we can look at? Combination of window attachments. So now that we have the 100 Douglas blinds and the low-E storm windows, what type of combination of attachments can we test in lab homes, and then what kind of savings can we see, and how does that affect the envelope, and yeah, assessing the durability and unintended consequences, and ... So I guess this goes about saying, what is the durability of some of these low-E storm windows, and what's the lifespan of them? These things all need to be tested. And then with that, I think that's it. So we have questions.
Yeah, thank you to our presenters. We have time now for a few questions. We have a lot of great questions from the audience, and I don't think we're going to get to all of them, but we will answer as many as time allows. The first question for Katie: in the testing that was being discussed today, did the test include infiltration performance among different types of interior storm windows?
The testing that we did for interior storm windows in the lab homes, I'm assuming was just the low-E interior storm window panel from Quanta Technologies. So there were no other types of interior inserts or panels that were tested.
Okay, great, thank you. Tom, we had a couple of questions about condensation problems, both on exterior panels without any vents and whether there was fogging, and someone else had seen condensation problems on new exterior panel storm installs, and they were wondering if you had any comments on that.
Yeah, so condensations, basically the issue you're trying to deal with is you have warm, moist air inside the home, and you want to prevent it from hitting some cold surface in forming condensation. And so the general rule is whatever is to the inside of the home as tight as possible. So if you're adding a interior low-E panel, those are designed to be very airtight, so they will improve your condensation resistance. They're making that inner surface warmer so you don't have condensation form on the side facing the room, and also by being airtight, it prevents warm air from getting into that space and forming in the cavity in between. Now for exterior storm windows, it's the same rule. You want whatever's inside to be tighter than what's outside, so that warm, moist air doesn't get to the cold surface, and if there is any moisture in that space, it's able to be vented. So what that means is you do want to, if there's any obvious leaks in your existing window, you want to, caulking or whatever, you want to do whatever, air sealing you can on the primary window. But that's also the reason exterior storm windows have those weep holes, not only to, if there's any sort of mass liquid from rain or whatever, but it helps to prevent that formation of condensation between the space. In either case, you're improving the condensation resistance of the surface facing the homeowner. So like in my home, when I added a panel, I used to get ice formation. I'm in Wisconsin. In the corners, you add a panel, you no longer have that ice formation. But that's why you have to make sure to stop this. I think someone mentioned fogging. You want to make sure those weep holes are clear on the outside panel.
Okay, great. Another question for Tom. Is there any consideration given for climate or latitude relative to low-E storm windows in the NEEA decision to support them as proven? It seems that climate and aspect tuning should be part of that decision since passive heating may be desirable in northern climates.
Yeah, and that's a very good point. So I showed the map and some of the calculations we did for the different climate zones across the country. But for the work for the Northwest and the RTF, we used some of the same results for the different cities in that area, but they have their own kind of definition of subzones, and they took our calculations. They also have their own tool where they do their own calculations for some of these different subzones, and that was considered. And to your point about the sun is your friend in the cold climates in the wintertime, they actually put in a provision that it must be a low E storm window, so emissivity less than a certain amount, and then we have a list of what products meet that, but also it has to have a minimum solar transmittance, so you don't want the solar control low E glass option. That's very good for down south. It's not what you want in the Pacific Northwest. So it's in the details in the specification, but they did account for that regional difference. So, and that would apply to any of the northern zones across the U.S. as well.
Okay, great, thank you. Joe, we had a couple questions for you on the lab homes. One of them was, do the interior storm windows open, or did they have to be removed to open the primary window?
So these Quanta exterior storm windows were operable. So they're designed to, if you want to open your primary window, you can actually slide the interior storm windows on a track and then open your primary window. And that's one of the good things about this particular interior storm window.
Okay, great. And then another question on the lab homes. Did the lab home testing measure only the center of the glass, or did it include infiltration measurement?
So yes, we did do some infiltration measurements if we're talking about the tightness, right? Yeah, so we did do a blower door test prior to the installation of the interior storm windows, and we did see a reduction in infiltration associated with the installation of the storm windows, but it was still within the margin of error of our calculations that we just decided to leave it out.
Okay, great.
And hold on. The primary reason for this is that the lab homes were already very, very tightly built, and the windows are the primary windows are tight. So in a home that was more leaky, the improvement would be seen in infiltration a lot more.
Okay, great. Thank you. Another question for Joe. How did the storm windows affect emergency egress from the home? Are they always compliant with fire code?
Well, since they're operable, I don't know. I'm going to defer to Katie on that.
I don't think they're designed to match the primary window, and so there's no change in any sort of egress issues.
Okay, great. Thank you. All right, so I think we should probably move on since we're running out of time here. Katie, did you have any closing remarks you wanted to make before we take our quick survey?
No, I don't think so. Just thank you for the opportunity.
Great, thank you. So now we'd like to ask our audience to answer 3 short questions about today's webinar. Your feedback will help us to know what we are doing well and where we can improve. The first question asks whether the webinar content was useful and informative. Please take a moment to choose your answer. All right, the second question asks about the effectiveness of the presenters. All right, and the third question asks whether the webinar met your expectations. All right, thank you very much for answering our survey. The next Building America webinar is on November 18th, and it will focus on high-performance HVAC systems, low-load HVAC systems for single and multifamily applications. You can also subscribe to receive notices about upcoming webinars and other news at that URL that's on the screen. On the behalf of the Building America program, I'd like to thank our expert speakers for their time today and to our attendees for participating in today's webinar. We had a terrific audience, and we very much appreciate your time. Please visit the Building America website to download a copy of the slides and learn about the program. We also invite you to inform your colleagues about Building America resources and services. Have a great rest of your day, and we hope to see you again at future Building America events. This concludes our webinar.